Okay, my name is Stefan Wolf. I'm talking about, I don't have it here.
Yeah.
Okay. So when I'm always looking here, it's because I'm canning to my slides and I don't have to. Yeah, I'm talking about open source HDL synthesis and verification with Yosys. And Yosys, of course, is a tool I wrote. I'm talking about a little bit about Verilog synthesis with Yosys. Then I'm talking a little bit about Project IceStorm, which is another of my projects. I've reverse engineered the bitstream format for the ICE40 FPGAs, so I can do something useful with Yosys. I'm also talking a little bit about Arachne-PNR, which is a place-and-route tool for the ICE40 FPGA. I'm talking for a very short time, hopefully, about my Pico RV32 CPU, which is a RISC-V implementation I made. But I'm not actually going to demo this, because when I wrote my slides, I thought I'd have like 40 minutes plus additional time for questions, and then I saw the schedule. And so I'm going to skip over some of the slides, and I'm not going to give you the live demo, but I'm still going to talk about it. And last but not least, I'm talking about the formal verification flows you can do with Yosys. Okay, so really quick intro to Yosys. Yosys is first of all, it's a Verilog synthesis tool. It's controlled by scripts, like this very simple script. We just use the Verilog frontend to read some Verilog files, and then just call the Xilinx command in this case to do synthesis for Xilinx 7 series FPGAs. And in this script, I don't even call it backend because I can say dash edif, and then I give it the edif file. It should write, and it will call the edif backend on its own. I really like this example, and if you have a couple of minutes later, I encourage you to go to the Yosys website and look into the description for some of the synth underscore commands, because they are just scripts themselves calling a lot of other commands. And some of those, again, are scripts that are calling the sequence of other commands. So it's pretty simple and obvious to see what sequence of transformation makes it possible to do this reduction of abstraction that essentially is synthesis, to go from something like an HDL code down to a gate-level netlist. I don't have system Verilog support, I don't have VHDL support, but I have a pretty complete support for Verilog 2005. Almost any Verilog code you have, chances are pretty good that Yosys will accept it out of the box. And if not, please file a bug report. It's really hard to test all that stuff and really get the last details of the language standard right. So if you have something that is Verilog 2005 and it's not supported, it's very likely to be considered a bug. There are only a few Verilog 2005 features that are not supported by Yosys kind of intentionally, like wired OR and wired AND, but most of it is supported. So, I not only have a Verilog frontend, I mean this is probably the most prominent part of the whole framework, but I also have a couple of other front ends, like a BLIF frontend for BLIF files. When you have a cell library in Liberty file format, then there is also a front end for that, so you can either import all the cell definitions as black boxes or as behavioral models, which can be quite interesting when you'd like to do post-synthesis verification, where you would like to go back to something that you can actually execute in a simulation environment or use together with the formal verification features of Yosys. There is also an internal format which is called ELANG, and I think there are a couple of things that are called ELANG for internal or intermediate or whatever. This ELANG file format can be used to do things like snapshots in a more complicated flow, but it's also very useful when you actually do development with Yosys, because it's pretty much a one-to-one mapping from the internal data structures to an ASCII representation. And sometimes it's much easier to just look at an ELAN file than to go through the internal data structures in a debug environment. Last but not least, there are also bindings to the commercial Verilog library. So if you, for example, happen to be in a company that already has a license to Verilog, then you can use Yosys together with Verilog, and then you have access to the Verilog VHDL, Verilog, and system Verilog frontends. For most people, the Verilog frontend of Yosys is like the big thing, but when you actually look at the code base, it's only a small fraction. So there are still many situations where you might want to use Yosys, but combine it with a different frontend. Yeah, likewise we also have backends. Again, you can write BLIF files, you can write DDIF files if you really have to. I'm not a big fan of this file format, but I think nobody really is. You can also write, there seems to be only a very small spot where I can stay out of it. There is, of course, also a Verilog netlist, which is a Verilog backend, which is useful for writing simulation netlists and other kind of stuff. For formal verification, you can write SMT2 files. This is the thing I'm going to talk about at the end of the presentation. But there are also other backends for formats like SMB or BTOR. Yeah, and of course there is a backend for this ELAN format, and other funny stuff like we have a backend for JSON. So you can dump the netlist in the JSON format, which can be quite useful if you just would like to script something and you happen to have already a JSON parser in your scripting language environment. Then this might be much easier than to implement a parser for BLIF. Also, there is a JavaScript Yosys port made with mScript, and so you can actually run Yosys in the web browser. And, my plan is to use this for educational tools to run in the web browser that we could use to teach people how to write Verilog code. Yeah, I think I'm going to skip over that. If you're going to try programming against the Yosys C++ API, you should look at this coding README file in the source tree. But most importantly, you should reach out if anything is unclear. There are few things in the Yosys API that are easy to use the wrong way, which is, yeah, of course, my fault. I'm absolutely aware of that. But at least until we have a solution for that, it's probably much better if you reach out early and not like build on top of an API usage mistake for weeks and then try to like redesign everything with it. So when you do ASIC synthesis, of course you can also do ASIC synthesis with Yosys, then you usually have a script that looks a little bit like that. I see, this is not actually... Okay. So, when you do ASIC synthesis, then you usually have a script that looks a little bit like this here, where you first have a generic part that just reads your design, and then does something like synthesis to the internal gate library in Yosys. And after that, you have a target-specific part like this here, where you try to map this internal gate list to whatever the target architecture is. In this case, I've chosen a flow where first map the flip-flops and then I map all the logics with ABC. There are different strategies to do that when you would like to do things like register balancing and retiming. This might be good to mention. There are two open source ASIC flows at the moment. I can't really answer any questions about them in detail because I'm just doing the Yosys. But they seem to be working quite well. There is Qflow and there is Coriolis 2, which is, I think, the successor of Liberty. So the entire flow for something might look like this, where you first call Yosys to do the actual synthesis, and after that, of course, I need a couple of other tools. Like in this case, because it's an IceStorm flow, I use Arachne-PNR as the place and route tool, and then I use two more commands that are very specific to the ICE40 floor. One is IcePack, which converts a text representation of what we want in the FPGA to the actual bitstream binary format, and then there is IceProp, which is just a tool that uploads the stuff to the FPGA. Yeah, so I think this is the best time to talk about Project IceStorm now, because we've just seen the script that's using it. So Project IceStorm is my attempt of reverse engineering the ICE40 FPGA. It's a complete written documentation of how the interconnect works. It's a little bit sparse, but if you know how FPGAs work in general, then there should be no problem with working through this and maybe an afternoon or something like that. ICE40 is a really simple architecture. That's one of the reasons why I chose it, because I also have other things to do. So Project IceStorm is this written documentation, but there's also a few tools that can be used to do low-level stuff with ICE40 FPGAs. Like there is this Icebox set of tools. These are Python scripts. Icebox Verilog, for example, reads a ICE40 bitstream file and generates a behavioral Verilog model of exactly that thing. And that was actually the first thing that I started doing this direction, and then it was pretty easy to like auto-generate hundreds of Verilog files, synthesize them with the Lattice tools, and see if the output of my Icebox Verilog is formally equivalent to the original code I put into the Lattice tools, and luckily I have a tool that can do formal equivalence checks. Yeah. So a little bit of history for this project. So a little bit of history for this project. I'm actually not the one I started it, but I gave it the name Project IceStorm. An acquaintance of mine, Matthias Lasser, started it last year and did stuff like the low-level bitstream format. So he then knew what bit in the bitstream format belongs to what tile in the FPGA, but not really what function this bit has, only this coarse thing. And he wrote the first tool that can take a bitstream file and just gives you useful information like bit 25 is set in this IO tile. And I built on top of that and reverse engineered the interconnect and the logic tiles and all the other stuff and created the tools and also the written documentation. Yeah, after that it was very, very easy to make the changes to Yosys. So Yosys works with, can synthesize netlists for this architecture. The only thing missing was a place and route tool, and Cottonseed wrote one, it's called Arachne-PNR. Right now it's a very, very simple simulated annealing-based placer, but we are working right now on improving on that and actually creating an analytic quadratic wire length placer that can be used as a first stage, and then we go to simulated annealing. But this is not implemented yet. However, with the current place and route tool, we have no known designs that don't route. But we also don't know how bad we are timing-wise because we don't have timing analysis yet. That is another thing I'm working on at the moment. Okay, but you can use Yosys, of course, to do synthesis for other architectures as well. So I've mentioned before there is a flow for designing 7 series FPGAs. We are also right now working on the flow for the C-Lego GreenPack 4 chips. As far as I know, this is the only kind of modern programmable logic device where the manufacturer just put a bitstream description in their datasheet. And this is not a typo, it's not a K missing and it's 25 kilonewtons. No, it's 25 lutz. It's a really, really small device. And from the synthesis part, it's a little bit difficult because those lutz all have different sizes. And this makes synthesis a little bit more difficult, but on the upside it's only 25 lutz, so it's almost impossible to write an algorithm that doesn't really perform well. So, yeah, this is the part where we don't have a demo. But please believe me, I can take my Pico RV32 CPU and synthesize it with Yosys and then run it on an ICE48K FPGA. A few sentences maybe about this CPU. It's a CPU I built earlier this year, and it's optimized for small size. It's probably not the smallest CPU on Xilinx 7 series. Depending on the configuration, it goes down to something like 750 LUTs. But probably you could make it smaller, but unfortunately you usually would like some memory connected to it, and then you'd like to I/O memory map some I/O, and on 32-bit address data bus, this easily takes another 200 LUTs or something like that. So I've more or less reached the point where it's not very useful, in my opinion, to further optimize the size. It's not optimized for high performance, so you see I have less than 1/3 BLIFs per megahertz. And I need a little bit more than 4 cycles per instruction, so it's not pipeline either. But it's optimized for high clock rate. And this is part of the easy integration thing, because I was kind of fed up with having a high performance design, then I need some kind of auxiliary CPU, and either I need some clock domain crossing FIFOs, or I need some kind of multi-cycle constraints to make the CPU run smaller than the actual computing core. So on Xilinx 7 series FPGAs, this one goes up to 570 megahertz, which I think is quite fast for a CPU. So you could also say, okay, maybe I need 4 cycles per instruction, but many CPUs clocked less than a quarter of the speed, so it's probably even better than a pipeline design on FPGA. But I'm not advertising this as, oh, use this for performance. I'm using this, and I'm advertising this for if you need something really small, then you can go for that. Yeah, and on the ICE40 with Yosys, it's about 1500 LUTs. With simplified core, it's about 1300 LUTs, so simplified core is still better, but it's not the word. With the Lattice synthesis engine, LSE, it's over 8000 LUTs, because LSE doesn't really understand how to map memories with 2 read ports to 2 parallel block ranks. Yeah. Good. Another thing we are working on right now is a little Raspberry Pi head with the ICE48K FPGA on it. And the main reason why we're building this is because we can then run all our tool chains on the Raspberry Pi itself, and then you can already demonstrate some kind of applications that wouldn't be possible with the commercial flow, because they're not available for the ARM architecture, but also usually the license would not allow you to bundle them with your device. Well, what could you do with something like that? I have this on-demand HDL generation. The idea is you'd have something like a logic analyzer, and you have a very complicated trigger condition. And in this case, you could just on-demand create an HDL that implements this trigger condition, synthesize and upload it to the FPGA. Okay. So, the last part of my talk, formal verification. There are a few things you can do with Yosys in this regard. The first thing is you can just use simple SAT solving. I'll show you some examples of that. This is very convenient, but also it's slow. So if you need something with much better performance, you might either want to export the design on the test. Now the battery is you can either export your design on the test as a BLIF file and then use some of the formal verification features in ABC, for example, or you can use the S&T backends in Yosys and then use that with an external S&T solver. Yeah. Let's go. Okay. So the first thing that helps here is that even though Yosys doesn't really support System Verilog, there are some features from System Verilog that I support in my front end, and one of them is ASCII. So you can do things like here. but I have a design with an A input, and if the A input is less than 0, then I invert it and design it to B, and otherwise I take it to this, and then I assert that now B must be greater or equal to 0. And then I can, and I think it kind of makes sense, right? And then I can run it through this little Yosys script. Just read it, -sv for system Verilog, otherwise it doesn't understand assert. It thinks it wants to instantiate a module named assert, and the module, the cell name is property. Yeah, some things you need to do to actually process this this thing and bring it into an internal representation that we can work with. And then I use the sub command to prove all asserts in this design, and then it comes back and tells me that I'm stupid, because when you have the smallest negative number in an signed integer, then you can invert it and it's still the smallest negative number in the integer. So my assert actually looks wrong. So another thing that is very important are meter circuits. So the idea is I have my circuit on the test, and I would like to convert it into something that has just one output, and if my properties are violated, then this output goes high, and otherwise the output stays low, and then I can pass this into some tool, and it says, whatever I do, this output never goes high, and then I have proven my asserts. Or it will tell me, this sequence of inputs will actually cause your output to go high, and then I know somewhere I screwed up with my asserts. So in this case, I have something with a 64-bit state variable that I initialize, and I then pass it through XOR shift 64 star, and this is actually a random number generator, and the cycle of that must be 2 to the 64 minus 1, and the only thing excluded is 0. So when I start with something that is non-zero, it never can become 0, or at least that's what the theory says. But now I can use this, no feedback. Now I can use this meter command. Now I can use this meter command and say, here is my module. In this case, I would like a meter circuit to prove my asserts, and then it modifies my design so it is this circuit with only one output that goes high when the asserts are violated. And then I write this as a BLIF file, and then I can use, for example, ABC to prove the assert too, in this case. So we've seen the sub command 2 slides before. I've proven that the most negative number stays the most negative number when you invert it. These are just some examples of what you can do with the subsolver. You can do bounded model checking and just say sequence of 50 time steps, and then it does its thing. I can run temporal induction proofs if the internal state of my circuit is either small enough or structured in a very specific way so that this kind of proof succeeds. So a lot of things can be proven like that. For other things, you have to export it and then prove it externally. You can write traces as VCD files and can look at them in GTK for whatever tool you prefer. You can also write sub-problems in the DMAX format, which can be interesting for profiling external subsolvers, and then make a decision based on that, what kind of subsolver you'd like to support here. It's possible to extend this and use different subsolvers with the same eGSMT engine that I built here. Yeah, you can do interactive troubleshooting with it. This is what I primarily use it for, that I have a design and then I test it and I see, something happens, and sooner or later I find this, via X, Y, Z, via never 1 becomes 1. How is this possible? And then I can just write a little comment and say, subsolver, give me any sequence of 15 time steps that has level 1 set to 1 and time step 10. And that's quite useful for troubleshooting. I always also wrote a framework for formal equivalence checking that can use hints like net names and so on to partition the circuit into much smaller circuits that can then be tested for formal equivalence. And for example, if you're writing a synthesis tool, this is really, really useful because you see I have some paths, and in one design it doesn't work, the design doesn't work when I run it through the parser. With this I can very quickly narrow the error down to one subcircuit that is now not equivalent anymore to the state it was before. And what it does here, I think it's too small to really see. It like creates a circuit that contains both circuits I'd like to test for equivalence. And whenever it finds a net name or some other hint that says, okay, this point should be equivalent, then it will add an equivalence cell and replace all users of those two wires that should be equivalent with the output of my equivalence cell. So this equivalence cell is like a buffer, but a buffer with two inputs, but the inputs must always be the same. And then I can use various commands that follow different strategies to prove for each of those equivalent cells that their inputs must be equal. And so this works really, really great to just narrowing down what you're looking at to one small subcircuit and then have like 20 cells to look at and say, what went wrong? Okay. Yeah, last but not least, formal equivalence, no, not necessarily formal equivalence, but formal verification with SNT-LIT. So SNT-LIT is a language to describe SNT problems, and it's used in the annual SNT competition. And that's great because that means every SNT tool supports this as an input language because they all would like to partition in the annual SNT competition. So I have no lock-in on any single SNT solver. You can use any SNT solver with my flow. And what I do, I have a little example here. It's not more or less trivial. I assume that the input always has the least significant bit set to 0, so the input is always even. And then I add the square of this to my memory set. And if I square an even number, then the square must contain 2 in its prime factors twice, so it must be divisible by 4. So both these significant bits must always be 0. And then I have another user script here with the SNT backend, that's the last line, this long one, where I say use the SNT big vector theories, export memories as SNT arrays, use this template file and write this SNT file. And then I can run an SNT solver like set3 on this, and in this case it tells me answered, so there is no input that actually breaks my assumption that all memory cells always have the 2 least significant bits set to 0. And this is what the template looks like I'm using here. And I'm not going to go into much detail here, it's just, it's SNT, and I begin with setting the logic. It's QF, AUF, BV, which means quantifier-free arrays, uninterpreted functional bit vectors. These are the SNT theories I'm using to encode my problem. And then I have this double percentage sign, and this tells Yosys to insert everything it creates in this line. And after that, because I have a module called main, now I have a type, you would call it, it's called sort in the SNT terminology. You have a sort called main_s that can represent the state of this circuit. In this case, I'm doing a simple bounded model checks for like 21 states, so I declare instances of this from 0 to 20. And then I add some asserts that encode state transitions that say whatever you give me, there must be a valid state transition from state 0 to state 1 and from state 1 to state 2 and so on. Then I tell it S0 is the initial state because I have an assignment I need to do. And then I create some more asserts to make sure that the memory is all initialized with zeros. Then I say my assumptions must hold everywhere. And finally, I'm saying, and also I'm looking for a solution where at least in one time slot, at least one of the asserts is violated. This is this last assert. And if it's answered, it's probably because of this, but maybe because I screwed the rest up. Maybe it's not even possible to satisfy all my assumptions. Yeah. Good. I think. Yeah, in the Pico RV, there are 2 examples that use this very in a much more advanced way to check for equivalence between the Pico RV and all its different configurations with dual port register file and single port register file and so on. It's probably worth looking at. So, Are there any questions? So, see here, first question.
Well, this is not so much of a question, just want to say that you have basically recreated like a dozen of either tools that have been proprietary before, and it's such an amazing effort.
Thank you. So I have to say, most of those proprietary tools share a large percentage of their code base. So when you have a synthesis tool, it's not really so hard to extend this towards, for example, formal verification. And at the same time, it's so useful to have all these tools when you're writing one of them. So.
How come the memory that is like 6 gigabytes each?
I have no idea.
Maybe I don't need it. Just wonder, do you infer memory and stuff like that?
Yeah, I can infer block memory in the FPGA flows, in the Xilinx flow, and in the IceStorm flow. With the Xilinx flow, there are some situations where I don't recognize transparent read port, and then the read port will be asynchronous. Yeah, I think that's nitpicky. I support instantiation of block RAMs, and it's really, really easy to write your own descriptions. What does your block memory look like, and make users infer those block memory resources.
I have a question regarding, so you have your front end now, and I think Verilog has a front end, and you have intermediate representation, they have one. Is there like, I think it's not provocative to say like, wouldn't it be good to have something like an LLVM for HDL designs or something?
I would agree, and I'd say that at the moment more than one tool that would like to become the LLVM of synthesis or HDL or whatever. I looked into the existing Verilog frontends, specifically I did look at Eco's Verilog and Verilator, and decided that they're written for a simulation engine, so they support a much larger subset of Verilog, and at the same time they create a representation that is really aimed at simulating it at the end, and not really aimed at creating a netlist. So in the end I decided maybe, because it's also not invented here, it might be a lot of time to read all that stuff and yeah, get really grasp of all the details, so yeah, I wrote my own. But then at the same, as I said, the Verilog frontend of Yosys is only a really, really small fraction of the whole project. And if someone comes along and says, now I wrote the universal HDL frontend and we can do Verilog and system Verilog and VHDL, I'll be happy to write bindings for that. Right now, the only way to do that is by using the commercial verification.
Okay, sorry, I have the mic. I wanted to ask a bit more about your proofs, proof system, because that I find really interesting. You had some pretty simple examples, and
yeah.
I understand, so your satisfiability verifier is probably able to deal with that. I was just wondering, how well does this scale up? Could I actually use this? I already write lots of assertions.
Well, it really depends on the kind of core you're simulating. And my experience so far is I have communication cores where I simulated that. I run bounded model checks that are 200 cycles long. That's not a problem. It's a different story when you start simulating things like CPU cores, because they have much greater freedom of what they do in each cycle. So maybe I should go back to this, yeah. So I have these two tests here, and one is the synchronous test, which says I instantiate two of those CPUs, run them in parallel, say they must start out with the same memory content, with the same register file content, and with the reset enabled. And then I'll see if they do the same. And then I run them synchronous, then I can simulate like 13 cycles in 10 minutes. And after that, it pretty much stops, and then maybe after 2 hours, it's 60 cycles, something like that. So this explodes. And similar for this here. So in my experience, this really depends very, very much on the design, and in some designs you can easily run thousands of cycles in a bounded model check, or some other things, and it just explodes in your face. Sorry, I'll just keep doing this here. Yeah, most of this formal stuff is related to write backends. And it's really easy to write a user's backend. So if anyone says, I know the RISC-V people, for example, use HOL4 at least for something. A lot of people use Haskell for various formal things. If any of you ever say, this is an interesting problem, if I only could convert my Verilog into a Haskell description, please contact me. It's really, really easy to write it. It's much, much harder to get a grasp of what it could do with Haskell in a formal environment. So I can't do it without anyone externally giving me like a set of features that are required and what should the output look like.
Sorry.
Does this answer the question?
Yes, but I have a follow-up.
Yeah.
Follow-up question. So you're trying, as I understand it, every cycle you redo the
Test.
Could you repeat that because of the video?
for the video. Repeat.
Start again.
Okay, so what you just described, every cycle you try and prove the asserts again based on the previous state, yeah? So the complexity increases in every cycle.
It depends. In the thing I just showed you, this is the probably most stupid way to do it. I just say, look at all the 20 cycles at once and tell me is there an assert anywhere that fails.
Oh.
But this was just an example and I wanted to fit it on one slide. Usually would set up something like that as an incremental proof, where I first say, is the assert violated in the first step?
Yes.
And if it's not, then I can turn it into an assumption and say, I'm assuming there is no way it can be violated in the first step. Now do the same thing for this longer proof that looks for violations in the second cycle. The built-in subcommand can do that, for example. And you can certainly do it with the SMT flow, but because you have to specify a template, you essentially have to set up the proof and say what to do. In the more complicated proofs, like the one I mentioned here, I have a Perl script that just remote controls the SMT solder. And I wrote a little Perl. I don't like Perl. Python script. And I wrote a little Python library that can be used to simplify the step of describing the proof strategy. I have on my to-do list to kind of extract from that a generic thing to do just bounded model checking, because this is a so important kind of proof. But you don't lose the generality of just being able to give the SMTs or whatever you'd like to do.
Time for one more question.
A couple of questions.
Just so it's not technical question, so I'm not in your community, so maybe it's obvious for you, but for me it's very much interesting. Is it your hobby? Is it your private activity outside of working hours? I didn't catch it from your email, from my presentation.
So, I always like to think of myself as something like a researcher without an affiliation, and I'm like self-funding my research. So you could say it's my hobby, but to be honest, sometimes it feels too much like work, so I don't know if I feel comfortable saying it's just my hobby. But I do it in my spare time. I have nobody paying me to do it, but I do a little bit on consulting work because a lot of people are now using this and building like commercial tools with Yosys as the backend. $20 in Ecos, where I look at least $50 in all kinds of tools, the commercial tools and the free. And the like.
Julius, I do have a question, sorry. Quick question. Have you asked the major FPGA vendors for collaboration? And I'm anticipating that maybe they're not so keen, but is this something that the foundation could help with, to channel a request to Ultra and Xilinx?
I'm in touch with some people from Xilinx, but on a completely different topic, because they are also using my Blockhammer tool now to test Vivado. I think someone of our group reached out to the vendor of these green pack chips, those with the 24 LUTs, because they're kind enough to document the bit stream, but they didn't document the upload protocol. I mean, I have no idea what. I'm not really afraid of reverse engineering that, honestly, but and they also have no HDL tool at the moment. So with their tool, you can only draw individual lookup tables and then connect them. So maybe there will be some collaboration there. I have not reached out to Lattice yet. Also because I don't really know how they think about my reverse engineering work.
Should be 8,000 LUTs versus 2,000 LUTs.
Yeah, but it's, I mean, I could probably rewrite my HDL in a way so it could work around this limitation of their tool.
Oh, that's it. Thank you, Clifford. Cheers.